Hi, I'm Martin. This video is about local symmetry groups, which are symmetry groups assigned to an atom or part of a molecule, sort of like molecular fragments. If you're like me and you enjoy chewing gum, you've probably been in contact with the compound xylitol. This compound is interesting because, as you can see, it is achiral, since the two groups from the middle carbon are mirror images of each other. But still, if you switch the alcohol group and the hydrogen group on this carbon, you get ribitol. Ribitol and xylitol are diastereomers of each other, and they're examples of something called pseudoasymmetry, which isn't a very good term since they are clearly symmetric. But this term isn't used very much nowadays. Now, we more commonly use stereogenic center, which is an atom where switching any two of its substituents lead to stereoisomers. Along with the chiral center, these terms can sometimes be confusing, and it can be useful to use local symmetry groups as a way to determine the outcome of a substitution. So let's begin. Symmetry descriptions of entire molecules are given through point groups. Point groups are found by considering the symmetry elements such as mirror planes, axes of rotation, or improper axes of rotation. And parts of molecules can also be assigned local symmetry groups, who are also given by point groups. The local symmetry group will always be a subgroup of the molecular point group. So when we look for local symmetry, we should only consider the same symmetry elements as the entire molecule. However, to determine the symmetry elements for part or point in a molecule, we look for symmetry elements that affect the entire molecule, but leave that point or part invariant. It's just like looking for symmetry elements for the entire molecule, where your result should superimpose the original molecule, except the extra stipulation that the point or part are invariant. Let's look at some atoms in the norbornane. Norbornane has a point group of C2V. It has only one CE2 axis and two mirror planes bisecting either between the top two hydrogens or through them. Now let's look at a single atom within the norbornane. The top carbon atom will remain unmoved if we apply the C2 axis to the molecule. Therefore, the C2 axis is also a symmetry element for that carbon atom. In addition to this, it also remains unmoved by the vertical mirror planes. So this carbon atom's local symmetry group is also C2V. Now let's look at one of the hydrogens connected to it. Then the C2 axis would move the hydrogen to the other side, so it's not invariant. The same goes for the mirror plane between the two hydrogens. However, the mirror plane bisecting the two hydrogens on top does not move the hydrogen, so the hydrogen has a local symmetry group of CS. Now the interesting part of local symmetry is that if you substitute that part of the molecule with something completely different, the molecule's point group becomes that local symmetry group. We can use this to more precisely determine if a substitution leads to chirality, since chirality of an atom is defined as the atom having the chiral point groups, those being C1, Cn, Dn, and T, O, and I, who are less common. If we now go back to the xylitol, the point group of this molecule is CS, which comes from the mirror plane bisecting the alcohol and hydrogen substituents, but it does not have any rotational axes. Now if we determine the local symmetry group of the central carbon, this should definitely give us an answer to whether or not it is a chiral center. However, we quickly see that the same mirror that bisects the alcohol and hydrogen atom also leaves the carbon invariant, meaning the carbon is also CS, which is not one of the chiral point groups. So while interchanging the two substituents lead to a diastereomer, it is not a chiral center. This doesn't mean it can't become chiral. If we rather consider switching either of the side carbons, would it then become chiral? If we look at the local symmetry group of either of the carbons on the side, we notice that the mirror plane does not leave them invariant, meaning their local symmetry groups are C1. So if we did substitute either of the carbons, the molecule itself would adopt a C1 point group, which is chiral.